And welcome to Chapter 4, Probability, Section 4.4 on the multiplication rule. In this section, we're going to learn about the basic multiplication rule that is used for finding the probability of A and B, which is the probability that event A occurs in a first trial and event B occurs in a second trial. It's important, however, in the multiplication rule to note that if the outcome of the first event, which is event A, somehow impacts the probability of the second event, which we'll call B, it's important to adjust the probability of B to reflect the fact that A has already happened. It's also important to note here that the key word for the multiplication rule is AND, whereas the key word for the addition rule was OR. So here's the notation for the multiplication rule, and this is what it looks like. The probability of A and B in parentheses. And what that means is the probability that event A occurs in a first trial and event B occurs in a second trial. Another way of noting this is like this: the probability of B with a slash A. And what that is represents the probability of event B occurring after event A has already occurred. So the way I read this is the probability of event B occurring, given that, meaning that that's what this line stands for, the words given that, A has already occurred. So again, the probability of event B occurring, given that event A has already occurred. So here's the formal multiplication rule, and I'm sorry if it looks garbled on your screen, but what it tells us is that the probability of A and B is equal to the probability of event A times the probability of event B, given that A has already occurred. So just like we saw here in this lower notation, that is the second multiplier, and really represents the event A is represented by the probability of event A, and event B is represented by the probability of event B, given that A has already occurred. Okay, so in addition to the formal multiplication rule, we also have what you'd call the intuitive multiplication rule, which is essentially the formal equation restated. So what that tells us is when finding the probability that event A occurs in one trial and event B occurs in the next trial, you're going to multiply the probability of event A by the probability of event B, but you want to be sure that the probability of event B that you're using takes into account the previous occurrence of event A. So again, this is really just a restating of the equation that we talked about in the previous slide. So some caution: when applying the multiplication rule, you always have to consider whether events are independent or dependent, and you need to adjust your calculations. Now, for the most part, we are going to be treating events in this class as independent. However, it's important to understand what they are saying here. And events can be independent in the sense that event A has no impact on event B, or they can be dependent, where event A could have or does have an impact on event B. So an easy example that I often give for this is if I go to the store and I buy, on my first trip, I buy dog food, and on my second trip I buy orange juice. Those two things have nothing to do with one another. One has at least no meaningful impact on the other that you're aware of. Now, if I said on my first trip to the store I bought a dog, and on my second trip to the store I bought dog food, those two things are related. It is likely that my buying a dog impacted my need to buy dog food. So those two types of events would be related to one another. So although kind of a cheesy example, it sort of gives you a general idea of what we would consider to be independent events, meaning that they have no impact on one another, or dependent events, meaning that they do. So in the multiplication rule can be used for multiplying the probabilities of several events. It just doesn't have to be event A and event B. So in general, the probability of any sequence of independent events is simply the product of their corresponding probabilities. So although that sounds wordy, all it's saying that is that if you have a known probability for event A, and event B, and event C, and as long as those events are independent, meaning that they don't have an impact on one another, and again, for the most part in this class, we will be talking and doing examples with independent events. All you need to do is just multiply their probabilities together. There's no additional calculations that are needed. So the multiplication rule is very straightforward. You're just multiplying the probabilities together of the different events that you want to multiply together. There's no other additional steps. And again, the only other thing you need to take into consideration is whether those events are independent or dependent. And if they are dependent, you need to take that into consideration per the formal multiplication equation. So this kind of restates what I just said, so we'll just work through this pretty quickly. But dependent and independent events, so two events, A and B, are independent if the occurrence of one does not affect the probability of the other. Several events are similarly independent if the occurrence of any does not affect the probabilities of the occurrence of any of the others. And if event A and B are not independent, they're said to be dependent. So again, that's really just what we were talking about on the previous slide. So two events are considered dependent if the occurrence of one of them affects the probability of the other. However, it's important to point out that this does not necessarily mean that one of the events is the cause of the other, although it can be that. It just means that the probability of one or the previous occurrence of one event impacts the occurrence of the next event. So in this course, as I talked about, a lot of these calculations, especially for dependent events, meaning events that have impact on one another, they can be very cumbersome. And so there's a very common practice in statistics of treating events as independent when you have small samples that are drawn from large populations, because in such case it's very rare to select the same item twice. And so you don't really have to worry about whether they're dependent or independent for that reason. And so for the purposes of this course, all the examples that we're going to see are going to be independent, either independent events or events that we're going to treat as independent. So, and the basis behind this rule is the 5% guideline. So what that says is that if a sample size is no more than 5% of the size of the population, that you can treat the selections as being independent, even if the selections are being made without replacement, so they're technically dependent. So what does that mean? In order to understand this, we need to talk about what with replacement and what without replacement means. So let's talk about that. Well, we can actually talk about it in the context of this example, and it'll help it make sense. So here's an example of a multiplication rule problem. So suppose 50 drug tests results are given from people who use drugs. 44 of the people tested positive, 6 tested negative, and there were a total of 50 people tested. So if 2 of the 50 subjects are randomly selected without replacement, find the probability that the first person tested positive and the second person tested negative. Okay, so here we need to discuss what with replacement and without replacement means. When you think of bingo, so when a ball is drawn in bingo, the number is called and then that ball is out of play for the rest of that round. And that would be what we would consider without replacement, meaning the ball gets selected and then it's out of play for the rest of the game. Now, in contrast to that would be with replacement, meaning that the ball would get put back in with the other balls. Now, that would not work in bingo. However, if you've ever participated in a raffle that occurs over multiple prizes, Oftentimes in the fine print on the tickets, it'll say that your eligibility, or if you win one of the prizes, it doesn't make you ineligible to win others. And what that means is that even if you were to win a prize, your name gets thrown back in the hat to be selected for another prize. And that would be what we consider with replacement, meaning that your ticket goes back in and can be considered for the purposes of any future drawings. So now that we've discussed that, let's get back to our example at hand. So here, we're going to select 2 out of 50 subjects without replacement, meaning they are not going to go back into our group of possible results and totals for the second person. So we're going to find the probability the first person tests positive and the second person tests negative. So if we take a look at our table, 44 people tested positive out of a total of 50 people. So the probability that the first person tests positive is 44 over 50. And your second person was going to have a negative test result. Now let's look at our data up here. 6 people tested negative. Now, here's where the without replacement part comes in. We used one of our people for our first person who tested positive. So, we don't have 50 people anymore for our second person who tests negative. We're actually only have 6 out of 49 people now who tested negative, or who would be eligible to be part of this total to get your probability for your negative. So your negative result is 6 out of 49 people. And when you multiply those two together, you get 0.108 or 10.8%. So this is without replacement. I'm not going to discuss these 2 slides. This is an example that I find adds more confusion than it really adds clarity. However, this example gets into people being born on different days of the week. You're welcome to review it on your own, but again, I find that it's actually a fairly confusing example, and that the previous examples are a little easier to understand. Some people choose to use tree diagrams, and what a tree diagram is it's a picture of all the possible outcomes of a procedure. So basically what it is it shows you your sample space, kind of like we learned in section 4.2. So if you follow me here you have a true and false question being asked. Out of the true and false question, there's only 2 possibilities. A person can answer true or false. And that question is followed up by a 5-optioned multiple choice question. So for the people who answered true, they also have the option of having next answered A or B or C or D or E. And similarly for the group that answered false, they have those same options. So you have 2 for your first part here, times your 5 different options for your second part, and that gives you the number of possible combinations that you're looking at. So some people use these types of diagrams to determine their sample space, especially if it's a little bit of a confusing example. But again, this is just a technique that I'm showing you. It's not something that you are required to use while doing calculations in this section, but if you find this helpful, please use it as a tool to help you solve problems. Okay, so in summary, in the addition rule, the word or in the probability of A or B suggests addition. And here you're going to add the probability of event A and the probability of event B, but you're going to be careful to add it in such a way that every outcome is only counted once. In the multiplication rule, the key word is and, as in the probability of A and B. And here you're going to multiply the probability of event A and the probability of event B, but you're going to be sure that the probability of event B takes into account the previous occurrence of event A. Okay, and then this is just another little example a little diagram that kind of shows you the application of the multiplication rule. Please feel free to look at this and to use this if this is helpful for you. So that ends section 4.4 on the multiplication rule, which also ends our coverage of chapter 4. Coming up next, chapter 5.